Thank you for being here. My name is Ittetsu Yamaga from Shizuoka Professional University of Agriculture. Today, I'd like to give a presentation of my research. The title is Synergistic Effects of 1-MCP and Photocatalytic Technology on Post-Harvest Quality of Fig Fruit. The fresh fig is highly appreciated by consumers because of its unique texture and flavor. However, figs are extremely perishable and rapidly soften after harvest. In addition, post-harvest diseases such as gray mold and black rot easily occur during storage and distribution. In Japan, figs are harvested mainly from harvest to October, which is a hot and humidity season. Under these environmental conditions, fruit cracking and fungal infection frequently occurred, leading to severe quality deterioration. As a result, the shelf life of fig fruits is very short, usually less than 1 week, even under refrigerated conditions. Therefore, the distribution of Japanese figs is currently limited mainly to local markets near production area, and the export opportunities remain limited. Ethylene plays a critical role in fruit ripening senescence. To overcome these problems, new post-harvest preservation technologies are required. In this study, we focused on two technologies, 1-MCP and a visible light responsible TiO₂ photocatalyst. One of the established approach to ethylene control is 1-methylcyclopropene. 1-MCP works by binding to ethylene receptors and blocking ethylene perception. It's already widely used in many fruits, apples, pears, avocados, and is very effective for maintaining firmness. However, when it comes to figs, there are still relatively few studies. In particular, its combined use with other technologies has not been well investigated, and the commercial application hasn't yet been established in Japan. Another promising technology is photocatalysis, especially titanium dioxide-based systems. The use of photocatalysts in food preservation has attracted increasing attention because they can decompose ethylene through photocatalytic oxidation reactions on the catalyst surface. On the right, these catalysts generate reactive oxygen species which can decompose ethylene and also suppress microbial activities. What makes these technology attractive is that it's chemical-free and works continuously during storage. That said, the actual effects of photocatalysts on fruit quality, especially when used alone, are still not fully clear. Although both technologies have individually attracted attention in post-harvest research, little information is available regarding their combined application in fig fruit. Therefore, the objective of this study was to investigate whether the combined use of 1-MCP and TiO₂ photocatalyst could synergistically improve post-harvest quality in fig fruits. First, to evaluate combined effect of 1-MCP and photocatalyst on firmness and decay fig fruits. Second, to test these effects over 2 different years using fruit from different orchards. Third, to explore the electrical properties as non-destructive indicators of fruit firmness. In addition, we also examined electrical properties of fig fruits. Recently, electrical measurements such as impedance and capacitance have attracted attention as a rapid and non-destructive method for fruit quality evaluation. Changes in cell membrane integrity and electrolyte leakage during ripening may affect electrical characteristics. Therefore, we analyzed relation between fruit firmness and electrical properties. And finally, to examine how 1-MCP treatment affects aroma volatile compounds, we investigated the effects of 1-MCP treatment on volatile compounds using GC-MS analysis. You can see the materials and method. We used the Masui Dauphine harvested in Iwata City, Japan in September 2023 and 2024. The fruits were immediately transported to the laboratory at Sapporo. Fruits were treated with 1-MCP at 68 milligrams per cubic meter for 24 hours and then stored with or without visible light responsive TiO₂ catalyst. The photocatalyst TiO₂ was compatible with visible light, and the 405 nanometer light emitting diode was used as irradiation lights. The wind speed was set to 0.25 meter per second. The fruit were maintained in an incubator for 3 days after 1-MCP treatment. Storage was conducted at about 20 degrees Celsius and 75% relative humidity, which reflects typical ambient conditions in Japan. This gave us 4 treatments: 1-MCP plus photocatalyst, 1-MCP alone, photocatalyst alone, and untreated control. We measured firmness, wood firmness, moisture loss, decay incidence, peel color, electric parameters, and volatile compounds. The degrees of decay was rated on a scale of 0 to 3 based on physical appearance. Electrical properties were measured at multiple frequency using LCR methods. Aroma volatile compounds were analyzed by GC-MS for comparison between 1-MCP treated and untreated fruit in 2024. First, I will explain the results regarding moisture loss, fruit firmness, and decay incidence in 2023. The moisture loss did not significantly differ among treatment. However, in 2024, the fruit treated with 1-MCP showed lower moisture loss compared with untreated fruit. Regarding fruit firmness, the combined treatment of 1-MCP and photocatalyst produced the firmest fruit in 2023. Similarly, in 2024, fruit treated with 1-MCP maintained higher firmness than untreated fruit. These results indicated 1-MCP suppressed fruit softening in fig fruit. Decay incidence was also reduced by 1-MCP treatment. Particularly, in 2023, the combined treatment of 1-MCP for the catalyst significantly suppressed fruit decay. Before the catalyst alone shows some effects, but they were not strong or consistent. The 1-MCP and photocatalyst application independently improved firmness and reduced decay incidence in fig fruit, whereas years of experiment also played a role in these parameters according to a three-way ANOVA. When we ran a three-way ANOVA, when we didn't detect significant interaction terms, to further evaluate the interaction between the two treatments, we applied the Rimpill formula to assess synergistic effects. Using Rimper formula, we compared the observed effect of combined treatment with expected additive effects of single treatments. In 2023, the results were very clear. For decay incidence, the observed synergistic effect was 53.5, while the expected effect was 20.5. That's a strong synergistic effect. For firmness in 2023, the observed value, 55.2, also exceeded expected value 47.2. In 2024, synergy was observed for firmness but not for decay. These results tell us that although the photocatalyst alone had limited impact, it clearly enhanced the effectiveness of 1-MCP when used together. Next, I will explain ring color changes. In 2023, the changes in L star, A star, B star, and chroma values were smaller in the 1-MCP treatment. The two-way ANOVA showed 1-MCP treatment affected all color indices. Similarly, in 2024, 1-MCP treatment suppressed ringed color changes during stage. These results suggest 1-MCP delayed ripening progression in fig fruit. Since fig fruit rapidly changes color during maturation, suppression of ringed color changes is an important indicator of freshness retention. There you can see the result of electrical properties. The fruit firmness showed strong positive correlation with resistance and impedance. In contrast, capacitance and susceptance showed negative correlation with firmness. They are a unique aspect of this study. Furthermore, the fruit treated with 1-MCP showed higher resistance and impedance values than untreated fruits. These changes are likely related to cell membrane integrity and electrolyte leakage. During ripening, senescence, cell walls and membranes become damaged, causing intercellular ions to leak into extra spaces. As a result, electrical resistance decreases, capacitance changes. Therefore, electrical properties appear to reflect internal physiological conditions of the fruit. These findings indicated that electrical measurement may be useful as non-destructive indicators of fig fruit freshness. Aside from the correlations observed in fig differ from those previously reported in supplementary fruits, in citrus, wind puffing strongly influenced electrical characteristics, whereas in figs, softening and tissue breakdown are the major physiological change. Therefore, differences in fruit structure and ripening behavior may explain these contrasting results. Next, I will explain the volatile compound analysis. G-Chemist analysis detected 29 volatile compounds and 7 compounds showed a significant difference between treatments. In the 1-MCP treated fruit, several ester compounds such as ethyl butyrate and ethyl hexanate were reduced. These esters are associated with sweetened fruit aromas. Conversely, peak areas of 2-methylbut, 2-NR, nonane, and benzaldehyde in the 1-MCP treatment were greater than those in the control. Generally, ester production increases during fruit ripening. Therefore, the suppression of ester compounds by 1-MCP suggests delayed ripening. In addition, aldehydes are sometimes associated with plant defense responses and disease resistance. These results indicated that 1-MCP not only delays ripening, but also alters volatile metabolism. However, the fruit used in this experiment were already edible at harvest. Suppressing over-ripening is likely to contribute to maintain market quality. Discussion. These findings were generally consistent with previous studies that 1-MCP suppressed ripening, softening, and fig fruit. Importantly, the positive effects of 1-MCP were observed in both experimental years despite difference between fruit maturity and orchard conditions. Although the fruit harvested in 2023 appeared more mature, 1-MCP still maintained firmness and reduced decay incidence. This suggests that 1-MCP may be effective even under commercially realistic conditions, where fruit maturity is often variable. In contrast, the photocatalyst alone showed limited and inconsistent effects. Therefore, suppression of ethylene perception inside of the fruit appears to be more important than simply removing ethylene from the storage atmosphere. Interestingly, when 1-MCP and the photocatalyst were combined, the clear synergistic effect was observed for firmness and decay suppression. This synergistic effect is likely related to their different mechanism of action. 1-MCP inhibits ethylene perception inside the fruits, while the TiO₂ photocatalyst decomposes ethylene gas in the surrounding environment. In other words, one technology acts inside the fruit, while the other acts outside the fruit environment. Because these technologies target different stages of the ethylene system, their effect may complement each other and more effectively suppress ripening senescence. Another important finding was strong relationship between fruit firmness and electrical properties. Therefore, electrical measurement may reflect internal physiological conditions of the fruit in a rapid and non-destructive manner. We also found that 1-MCP significantly altered volatile compound composition, since ester production generally increases during ripening. These results support the idea that 1-MCP delayed ripening progression and suppressed over-ripening. From our perspective, this technology has potential for commercial application in distribution systems. One advantage is that the treatment was effective even under ambient temperature storage conditions. This may help reduce refrigerating costs during storage and transportation. In addition, the combined treatment maintained fruit firmness and freshness-related quality characteristics during storage. This could improve long-distance transportation and export potential for Japanese fig fruit. Furthermore, electrical sensing technology may contribute to smart agriculture system through rapid and non-destructive freshness evaluation.